Okay, let's go ahead and get started. So, hello everyone. Thank you for tuning in to another edition of NextGen Geospatial. My name is Jeffrey Gillen. I'm a data scientist and educator here at the University of Arizona. We are coming to you live from the Arizona Library here on the campus in Tucson, Arizona. And we are going to talk about cloud optimized point clouds today. So this is kind of a continuation from last week. Last week we talked about cloud optimized geotiffs. So this is very much in a very similar vein, only instead of geotiffs, which are two-dimensional imagery products, we're now going to talk about point clouds. And we'll get into all the details about what point clouds are if you are unfamiliar. So let's go ahead and get into the content here. Okay, so as usual, here on my screen is the course content for NextGen Geospatial. I just posted that link in the chat if you're interested in following along from here. You can find all of my sessions. And if you happen to miss us live, you can always find us on our YouTube playlist. And we have that. It usually takes about a week or so for the latest videos to get up on YouTube. But I believe we do have all the others previous 5 or 6. They should all be up in our YouTube playlist for now, if you're interested in checking those out. All right, let's go down to the schedule. Yeah, we are flying through the semester. It's already October 8th. Okay. So we're going to talk about cloud optimized point clouds, and I call them point cloud analysis design for the web. So let's go ahead and click into the content. And let's just start with what point clouds are. Some of you are probably familiar, others might not be. And so when I mean a point cloud, I mean a geospatial data product that was probably made either from LiDAR, which is light detection and ranging, or from photogrammetry. And so this is a very common thing that we're using either LiDAR or photogrammetry from a drone or from an airplane or even from an orbiting satellite to make a three-dimensional model of the land or the resources that are on top of the land. And so if you've never seen a point cloud, here is one. This is a point cloud made from photogrammetry from a drone. Flown over my colleague Tyson's house on the west side of Tucson. And so this is just made with a series of overlapping two-dimensional regular JPEG images from a drone, but through photogrammetric processing and some very nice software, we can make a very beautiful three-dimensional model. And a three-dimensional model that is accurate to scale. So you can measure things. You can make a point cloud, and then you can actually identify things or measure things, volume, height, length, width, whatever. And so point clouds have a lot of utility in land surveying. I've used them around forestry applications. I've used them around buildings, point clouds around rangeland monitoring, other kind of like environmental monitoring along rivers. It's just a really great way to make three-dimensional data of pretty much anything. All right, so that's essentially what a point cloud is. And we're talking about cloud optimized point clouds. So cloud optimized point cloud. Again, as I go through this material, don't try to read it as I'm scrolling through. For the most part, please just listen to my voice. If there's anything specific in here, I will kind of highlight it for you. But this material is written in a way where you can check it out and step through it yourself asynchronously. So cloud optimized point cloud, or COPC, it's the same idea as a cloud optimized geotiff. If you're not here last week, a cloud optimized geotiff is just a geotiff, but it's been rearranged in a way that makes it streamable across the web. And so what makes a COG, or a cloud optimized geotiff, very useful is that it actually has things baked in it that make it streamable. It is It has overviews and it has tiles that are already baked into the file format, which typically was the purview of a tile service, or like a web tile service or a server. So with the cloud optimized formats and technologies, we are actually embedding in the file format itself the ability to stream things, point clouds or cogs across the web in little bits at a time. And so the analogy that I like to use is around how we stream other media in our world nowadays. Like, how often do we download movies anymore? Not so much, because everyone's on Netflix streaming movies. And so we can do essentially the same thing with geographic data. Point clouds or COGs, cloud optimized geotiffs, can be sitting in cloud storage somewhere, and they can be sent to some application. It could be someone's computer, a website, Jupyter notebook, some kind of analysis environment where someone can work on it in real time. And instead of having to download all of that data, as we know, point clouds can be gigabytes and multi-gigabytes in size. We can just get little bits of it to play with. So that's essentially what a cloud optimized geotiff is. It's been rearranged to optimize it for working directly on the web. And we can look at a few examples. So I go to this here. Oh, Zoom stuff is in the way. Okay, so what you're looking at here is a cloud optimized point cloud. It looks just like the other point cloud we looked at. It looks just like a point cloud, but it's a little different because it actually is sitting in cloud storage of Cyverse. So that's where the actual point cloud is located. And I'm not sure how big it is. It's probably 4 gigabytes in size, but it's being streamed from that website, or sorry, yeah, from Cyverse data store into this web application where we are viewing it. And what's nice about it is it's not going to render all of the points all at once. So just like tiles and overviews, we can do a similar thing with point clouds. It's something called an octree organization. And so as you zoom in or zoom out, you're going to see different tiles resolve. So you can see that how it starts to be coarse, and then, yep, it gets resolved into something finer and finer. And so that's kind of the magic of cloud optimized point clouds, is that it's working kind of in a tile and overview kind of way. And so we're not having to force the entire 4 gigabyte file across the internet. What we're pushing across the internet is just what is necessary for the visual that we have, like what our zoom level is. And so that becomes a lot more efficient in getting data across the web. So yeah, so if I zoom into it, you can see it resolve. Yeah, so we're used to seeing this on like Google Maps or something. As you zoom in, you see the tiles start to populate. It's the same idea, only we're doing it with point clouds. And so this is a viewer, a cloud optimized point cloud viewer from the company Hobu. And so it's just like a really nice way to visualize point clouds. Anyone has the ability to use this visualization website. All I have to do is essentially give it a URL. Where is this point cloud you're trying to share? And if it's cloud optimized, then it will render it directly into this viewer. And then you can share a link and anyone can check it out. Okay, why is the flag on the green so pixelized? That is a failure of photogrammetry, is what that is. Yeah, so objects that are complex or thin or just have a really odd structure are going to be much harder to reconstruct with photogrammetry. So a big bolt, like a big rock or something, is very easy. A car is usually pretty easy. The ground is usually pretty easy. Trees are quite difficult because, man, they are just very complex things. And so same with a flag, for the green. It's a complex object, and therefore it's not going to come out reconstructed as well as we would like using the photogrammetry technique. So thank you for that question. Okay, so we gave an example of a cloud optimized point cloud. Let's see. Here's another one. This is a LiDAR, an aerial LiDAR point cloud. So I did not create this one. This one was created by probably some kind of vendor for the USGS. And it's LiDAR. This is Prescott, Arizona. It's coarser because it's from an airplane, but it's the same idea, is that it's a point cloud that is in storage in the Cypress data store, and it's being streamed to this web viewer, and we can view it in real time, and it's streaming it as we zoom in and out, kind of what it needs to show us where we are with our zoom. Okay. So who is using COPCs, or like how common is it? So COPCs is actually a fairly new format. I've only been aware of it for maybe a couple of years. The company that made it is Hobu. What do I have there? Yeah, I guess I don't have a logo. Thought I did somewhere. Anyway, yeah, here it is. Hobu. So they're the company. They're the ones who have developed the cloud optimized point cloud. And it's becoming more popular because people like what it can do, that I can stream stuff from cloud to any application, any website, any analysis environment. And what's great about it is it's an LAZ. So it's the same point cloud format that we are using already. So typically with LiDAR photogrammetry point clouds, we usually work with an LAS or an LAZ as a file format. And so this is an LAZ, which is a zipped file, and it's just rearranged in a little different way. Don't need to go into kind of the details of that. That's something you guys can dig into, but it's just been rearranged in a little different way to allow it to be streamed, point by point. And so you can stream cloud optimized point clouds into QGIS, for example. I have a little tutorial if you're interested in doing that on your own time. I'm not sure if ArcGIS Pro or Esri is able to read. Well, they're able to read them. I'm not sure they are writing out cloud optimized point clouds yet, but I imagine if they are not yet, then they probably will be soon. I'd have to kind of research, where they are with this cloud optimized technology. ArcGIS can absolutely read and write cloud optimized geotiffs. I know that for a fact, but point clouds, I'm not quite sure. But I know ArcGIS can read them because it's backwards compatible. So any software that can read a LAS or an LAZ should still be able to read a cloud optimized point cloud because it's essentially the same format. How do we create cloud optimized point clouds? Well, we use a software program called PDAL, which is also developed by the company Hobu. And so PDAL is similar in a lot of ways to a different software program called GDAL. So it's just a command line tool. So there is no graphical user interface. It's something you just do on the command line, but it's got a lot of power. And one of its abilities is to create these cloud optimized point clouds. And so I believe I have a little tutorial on how someone would use PDAL to make, take an existing LAZ that they have and then convert it into this cloud optimized format. We're not going to do that together. We're going to do something a little different together. So right before we get there, though, we have to talk about another format called entwine point tile. Perhaps maybe if you're in the geospatial world, maybe you've seen EPT or entwine point tile. And from my understanding, it is essentially the previous generation of what a cloud optimized point cloud is now. So it's the exact same idea. Only it was, instead of it being a LAZ that's been reconfigured, it was mini files, think mini like JSON files or something. So it was the same idea and accomplished the same thing, maybe in a little less elegant package. And so Hobu has come out with the COPC as I think basically as a replacement for it. If anyone has more knowledge on that, I'm happy to hear it. But I think that's pretty much what I've gathered. So entwine point tiles and COPC essentially do the same thing, but COPC is like the latest generation, and it's a little more elegant, and it comes in a LAZ format, which is like an industry standard around LiDAR point clouds.
Well, the only way to create these point clouds?
Currently, I think so. The question was, is PDAL the only way to create the cloud optimized point cloud? I currently think so, but I feel like this is taking off in the kind of the open source ecosystem of geospatial tools. So yeah, it seems to be early days for the COPC, but I know a lot of people are kind of excited about it. Okay, so the entwine point tiles, we are actually going to do an exercise using them. Just like in the several of the past workshops, we're going to use a Jupyter notebook. There's existing Python code that we're going to click through. So it requires no actual typing or programming ability. All you have to do is click boxes in a sequence and we can see what the Python code does. We're going to run this in a hosted instance called Google Colab. And so we're going to run our Jupyter notebook on Google Cloud's infrastructure. And you guys are with me, following along. You can just click this button here to open the Jupyter notebook in Google Colab. And so what we're going to do is we're going to use USGS LiDAR, and it's been put into this EPT format. And so I'm using it just because it's an existing really great notebook that shows you kind of the power of the cloud optimized technology, but it's still in the old format of EPT. So the same thing we're doing could probably be applied to the newer generation cloud optimized point cloud. But yeah, it still will give you the idea of what is possible. Okay, so what are we going to do in it? Yep, we're going to use LiDAR from USGS. And we're going to, looks like we're going to generate some DEMs. Yeah, based on user-defined area of interest, which is, yeah, so this is a pretty fancy Jupyter notebook. My Python programming is not nearly as good as what we will see here. So I must give all credit to Open Topography. They are the entity that has made this this notebook and a lot of others like it. So thank you, Open Topography, for making this available to us to use. So let's go ahead and open it and we'll get started. Okay, so we're not doing any machine learning. So we don't need a GPU. Yeah, so if you've never actually seen this interface before, let me just go over it real quick again. What we're looking at is a Jupyter notebook, which is essentially just an environment to write and run Python code, but we do so in a browser. So we're looking at this in Google Chrome. This Jupyter notebook, which it's called IPYNB, is like the extension for a Jupyter notebook. We are viewing it in Google Colab. And so I'm using Google's infrastructure and I get a little bit of free allocation to do so. So it's great for teaching and training, but if you want to do, actual research or something a bit more, you will either have to pay Google or find a different platform, like your own machine could work, or you could use Cyverse. There are several options. So I will just go ahead and connect to My resources, I'm just going to use your basic vanilla CPU. And looks like I have 12.7 gigabytes of RAM. Got some disk space. I'm not sure why half of it has been used. Maybe does it retain disk space over time? Maybe. What do you think, Carlos?
Just scratch space. We'll delete every one.
Yeah, so in my disk, it says I have 40. Oh, it's going down. It says I have 41 of 107 gigabytes. Like, okay, I guess I don't need that other 70. I don't know. Okay, so there, we're not going to go through every single bit of text here. They made a very, very detailed Jupyter notebook, which never in my wildest dreams could I make something this explicit. But it's really fun to do it and show the power of the cloud optimized point cloud technology. All right, we're just gonna skip all this stuff. So wait, running Colab. Okay. So we are essentially going to, we're just going to run this this cell here. It looks like this is going to install. Yep, we're going to install a bunch of things and import. We're just going to set up our environment essentially. So as I'm clicking through this, please don't focus on every line of code. Because importantly, I don't know what they do. Let's be honest. I know the big picture of what it's trying to accomplish. And so let's just focus on that. Okay, yep, it wants me to access data from my Google Drive file. Should I do that? Yes, I think so. I think that must be where it's depositing outputs. If I hit no thanks, I don't know if it'll work. Let's see, let's just do it. Sure. I know. Is that what did I just agree to? I think this will take a minute or two. So essentially what we're going to do in this notebook is we're going to find some LiDAR data from the USGS. So the USGS has made LiDAR data into the EPT format, and it's sitting in cloud storage on Amazon, I believe, so AWS. And so we're just going to tap into it. We're going to be able to make ourselves a little area of interest. Okay, and then we can pull the point clouds to us instead of having to, yeah, I know, I feel like I have a problem here. Same thing. Okay, your runtime will restart automatically. Do not rerun above cells. Okay, maybe that's part of the plan. What do we have in the chat here? It won't work. Yeah, I think Dan, I think the access to Google Drive is about an output, perhaps. They're not like taking data from you. I think it's more like once you create something, they want to put it there in your Google Drive.
It was also saying they were going to install Drive for desktop, and I used to have Drive for desktop,
Well,
and
let's just
I
keep
had
going.
trouble backing it up.
I think that crash is all part of the plan. Are you guys able to continue on the next cell? No? Okay, well, we'll just,
Oh, it's going now. So you just have to be patient. It's taking a while, but it's finally moving.
yeah, this is a very heavy notebook. They kind of overdid it. You're able to continue? Yep, okay. Yeah, I'm on cell 2 here. Still going.
So very fun.
Yeah, okay. Yeah, it just took some time.
Yeah.
Yeah, the crashing on the first cell was like, that is what it's supposed to do, apparently.
So what's the reason that it's supposed to crash?
They're restarting the kernel. So you're installing things and then they need to like refresh and restart the kernel for those installations to take effect. Okay, well, let's keep going. I know some of you might not be able to accomplish it in real time. That's okay. The notebook is there if you're interested in learning about it on your own time. We'll also have this video in about a week if you want to just watch what we end up doing. That's fine also. Okay, we'll just go past this local install. We're not going to do that. Okay, we have a whole lot of modules to import. So again, I guess it's still part of the setup. And we're using lots of stuff, GeoPandas, NumPy, OSGeo, PDAL. Okay, and then they do a huge amount of function defining. We're just gonna hit play and go on past all of it. Wow. It just keeps going on. Okay, now we're into stuff we might be able to understand. Okay, so this says we're going to get a GeoJSON file for the 3dep outlines from a URL. Okay, so 3dep is 3D elevation program from the USGS. So that's the name of their program for their LiDAR data sets. And so there's actually an existing GeoJSON which shows us where all of those data sets are in the United States. That's a starting point, basically. Okay, okie dokie. Then we're going to create an interactive leaflet map. And we're going to be able to, on the map, actually decide where we would like to get LiDAR data from. Yep, so the options are you can upload your own shapefile. Let's not do that. Instead, we're going to, create this like interactive kind of thing, a little map that's kind of fun. So to define a corridor, so how this works is you basically just draw a line. So 2 points, or maybe it's more than that, but you basically draw a line and then you decide how wide the line should be. It could be 100 meters, it could be whatever you want to do. And then you're going to pull all of those data points into our environment here, and we're going to look at them. So it's all about just showing the fact that we can choose a small area of interest and not have to download gigabytes and gigabytes of LiDAR. We can just choose a little area of interest and interact with that instead of the entire LiDAR catalog. Okay, so I believe we still have to run this cell either way. All right, so we are going to do option 2, which is going to produce an interactive map using leaflet, IPy leaflet. Wow, they have a lot of important notices here. I'll just go past those and hit play. It's the beauty of Jupyter notebooks. You can just hit play, hit run, and figure out why the code works at a later date. Okay, so this is what it has created. So here I have a map of the United States, an interactive map right here in our Jupyter notebook, which I think is pretty fancy. And then in here, we can select the area we would like to look at around point clouds. So keep in mind though, if you choose a really large area, it's not going to work so well for you. It's going to do what you tell it to do. So if you're like, I would like the LiDAR points across all of Pima County, that's going to be like billions. It's not going to work. So I would suggest a very small area. So let's zoom in to a very small area. So let's go down into Tucson. Okay, so here I am kind of on the west side of Tucson. So here's the University of Arizona. Should we make a point cloud just like right through the middle of campus? Yeah, let's do something like that. So for me to select an area of interest, we're using this polyline tool. So in other iterations of the notebook, they allow you to do like a polygon, but for this one, it's about corridors, and so they want a line. And so we'll take our little polyline here, and then I can draw a line right across campus, right across the football stadium. Okay, and how do I finish it? Click last point to finish. Okay, so I've made a line, so that's my area of interest. I would like to extract or get the points along this line. And those points are sitting in Amazon Web Services server somewhere in the world. Don't know where they are. Right, so after you've made your little area of interest, this is where you specify how big of a buffer distance. And so by buffer, it's like, okay, I'm going to get the points from the line, but then like how wide is the line is what buffer distance is referring to. So again, I would make it small, I don't know, 100 feet or something. What do they have here? So yeah, run this next cell and enter the desired buffer distance in meters in the text box. So would this be this thing right here, value? I think so. So I'm just gonna run the default. So I think it's description buffer. Yeah, so I believe it's 50 meter is the buffer distance. That's what it's asking you to do. Does that make sense, Kamal? Yeah, 50. So if you do something like 1,000 meters, it'll do it, but it'll probably crash your session because it's gonna try to bring in like 1 billion points. I'll just go ahead and hit run. Yep, 50 meter buffer distance. Right, we'll just click the next cell. I'm not exactly sure what that one does. Shapely objects for the corridor. Okay, it's doing some coordinates and projections. Because yeah, for the visualization purposes, the buffered corridor needs to be in WGS 84, which is a geographic coordinate system. Click run. Okay, next is to find a 3D depth polygon. Yeah, so now that we've made our area of interest, now it's going to run that area of interest against all of the existing 3D depth data that's in AWS. and then find anything that overlaps or matches along with that corridor and fetch it back to us. Dan asks, can you change the buffer distance in the text box, or do you have to edit and rerun the Python code? I think you can just edit it to whatever you want. I just ran 50 here. I'm sure you could just change it to whatever you want and hit run. Is that working, Dan? You mean the widget? You mean the interactive map?
Let's change it.
Hmm. Well, I'm not sure oh, you mean in here. Ah, okay. Oh, I have no idea. That's new. No, the widget displayed the Python. Okay. I don't know. I really don't know. That's new to me. I don't know. Never thought about that. Looks like you should be able to. Okay, Dan. Okay, we'll just keep clicking on the cells. We're eventually going to get to our point cloud here. So this thing we just ran is actually, yeah, looking across, I think, all of the potential products and seeing if they interact or overlap with our area of interest. Now we need to specify the point cloud resolution. Find area of interest for plotting purposes, make the IPY map, add intersecting 3-depth polygon to the map. Ah, this is very fancy. Just hit run. Yeah, it's like notebooks like these, you'd have to spend a while with to know exactly what they're doing. Okay. Okay, so it output my box, my area of interest box. Great. Ah, okay, here is it. Yeah, and so that's cool. Yeah, just like the previous widget, they make this little widget here that allows you to specify the kind of resolution you would like to get the points in. I would again go small, don't go big. If you go full, that's going to be, it says around 3 million points.
You made a mistake.
Did you? How?
I went full.
You went full?
went full.
No, yeah. I don't know. What happened?
No, it's thinking.
It's okay. It's still trying to. Yep. So note, LiDAR point clouds can get very large very fast, and the point counts provided are an estimate. Yeah, if you select high or full, it may crash your session in Google Colab. That's what it says. So I'm going to go mid. Okay, so that was, I guess, the final of actually getting the points at the resolution I want. Okay, the next thing, it's going to take these points and run it through PDAL, which is the software that we mentioned at the beginning, right? It's a command line tool for doing all kinds of point cloud analysis. And so it looks like they're going to take those points, run them through PDAL. And what are they outputting? How to work, Carlos?
Just
Doing some email stuff.
Okay, the purpose of PDAL must be, nope, I don't know. I don't know why they run it through PDAL. Pipeline from PDAL. Well, guess I need to spend more time with this. We just hit run. Yeah, this thing just keeps going on.
It keeps going.
Yeah, so I've looked at this 2 other times last week and I'm like, this won't be so bad. Okay, I think we're finally getting to like a visual here. So it's gonna make a digital elevation model from the points that we selected. And we're able to just get a little bit of those points because this is a cloud optimized format. Those points are sitting in Amazon web service storage somewhere. And we are just grabbing a little area of interest. Yeah, okay, so we're making digital elevation model. We can make a digital surface model. Let's go ahead and do that. Okay, and then it's making digital terrain model. So a surface model is points that represent like basically any points that represent the ground or a building. A digital terrain model is points that represent just the ground. So in theory, all of the buildings or trees have been kind of wiped away from the point cloud. At some point, it's going to show us these things, I assume. Yep, just keep clicking. All right, visualize it. Yes. All right, to visualize it though, we do need, looks like matplotlib, Rio X-ray. Does that look familiar, Carlos?
Yeah, we're reading.
Yep. Okay, when we create, it's gonna, yep, looks like it's gonna output TTM test corridor. Just keep clicking. Well, that was kind of anticlimactic. We finally get to the end and well, there's my area of interest and there's my point clouds. And so that should be a digital terrain model. Yeah, so the buildings have been filtered out. And what is it showing here? It's doing showing a histogram of the elevations of all of those points. Interesting. I not see the, I'd have to change a few things to make it the DSM, I think. If I did this, let's try. Nope, I guess I didn't define it up. Yeah, I'd have to do that. Okay, I don't want to figure that out now. Okay, there's our grand. All right, so what did we do? We USGS has point clouds in a EPT file format, which is a cloud optimized format. It's sitting in cloud storage in Amazon somewhere. We can provide a little area of interest, reach out and grab those points directly from AWS without having to download, however USGS has them in tiles or blocks or chunks. So we can bring just a little bit of data into our environment. And this big, ridiculous notebook was just showing us basically how to do that. I think I should take this notebook and just like trim it down to its essentials to get the idea. So this notebook is from Open Topography, and they have a whole bunch of other ones that do kind of similar things. They're basically wanted to kind of showcase things you can do with cloud optimize or EPT in this case, point clouds. And so they've got several notebooks that all do kind of similar things. So yeah, really great demonstrations, things that you can look at and kind of steal from if you're interested in doing this kind of point cloud analysis. And we had something in the chat. How do I get to it? There we go. Dan said, is including the buildings in the histogram, even though they aren't being displayed. Yeah, I'd say you're probably right. Yeah, if it were just the ground, why would there be such a large difference in the histogram? You would think it would be just the ground, right? Oops. Okay, well, that was a fun adventure. Going through that notebook. Okay, so that's what I want to show you guys today. You guys have any questions about cloud optimized point clouds? Like I said, it's kind of a new format. But I highly encourage you, if you are interested in taking data you are using or have created from LiDAR or from photogrammetry, it's a great way to share with people. And so if you have your stuff up in cloud storage somewhere, it could be Cyvers, it could be a server, it could be really anywhere. It makes it so much easier for colleagues to grab that data and use it in their own analysis or their own Jupyter environment, or whatever. USGS and the 3DEP program are kind of forward thinking around this topic. I don't really know of any other like institutions that are making point clouds like that, available in a cloud optimized format. Well, I mean, USGS is the biggest player around distributing LiDAR data. So I guess they kind of are the institution. Yeah, any thoughts or questions? You can ask it now, or you can hit me up later. Yeah, so I'll stop there. Actually, before I do that, and like what Michele likes to do, I like to go back home here and ask if you're able to provide a little bit of feedback. Sorry, this was such an adventurous one, but there's a feedback form here. And so we really do appreciate it. Any kind of feedback on any of the sessions that you've attended. We'd like to hear from you. How are we doing? What needs to change? What doesn't? Just, it's good to get some feedback when we teach these classes. So thank you very much for your kind attention. Let me put that actually in the chat. Copy link. Yeah, I believe that is the feedback form. It's put in the chat. So yeah, thank you guys all very much. And next week, what are we doing next week? Oh yeah. Next week, I'm going to do something called reproducible pipelines. So this one will tackle a few things. We're going to talk a little bit about scripting. We're going to talk a little bit about software containerization and how to string together scripts in a containerized way. We'll probably show something called Docker Compose. And we'll keep it pretty high level, but we'll have some nice examples so you kind of get the idea. And so the stuff I do with drones is like perfect kind of example of putting together several different scripts that can be all automated back to back to back. And so that's what we're going to talk about next week is reproducible pipelines. So I'll leave it right there. So thank you guys all very much, and we'll see you next week.